So this is a very short note about phase transitions in lipids and what properties we can measure in simulations to report on these phases. So just like any liquid such as water, lipids also have phase transitions. So what you're looking at here is a simple lipid membrane, a single component lipid membrane. On the y-axis is the heat capacity, and on the x-axis is the temperature in degrees centigrade. At low temperatures, lipids form what is called the gel phase or the solid phase. Here, lipids are perfectly aligned to each other, just like water molecules are in ice. They remain in their places, they do not move around too much, they do not diffuse long distances. If you raise the temperature, then you go over this little peak in the heat capacity, which represents a phase transition, and then you get what is called a ripple phase, which is similar to the gel phase, but now the lipids form ripples over long distances. Finally, you come to the main phase transition right here, where you have a very high heat capacity because all the energy being supplied is being not used to increase the kinetic energy, but to break non-bonded interactions that convert this ordered phase into a fluid phase, which is also called the liquid disordered phase. As you can probably imagine, diffusion of molecules inside the fluid phase is much faster than it is inside a solid phase or a ripple phase. Now, in the solid phase, if you look at individual lipids, they probably look something like this. So these are two lipids in the same leaflet. And as you can imagine from this, the lipid order parameters, the deuterium order parameters versus carbonate number, are fairly high. So let's say they go something like this, if it is a saturated lipid. And this is a saturated lipid because you can see that the phase transition is about 43 degrees centigrade. For unsaturated lipids, the melting occurs much earlier because of chain unsaturation. Because if one of the bonds is saturated, then the direction of the chain will change in this carbon-carbon double bond, and therefore alignment will not be easy. So saturated lipids freeze at much higher temperatures. A typical example of this is wax. Now, when you reach the fluid phase, the lipids actually look very different. They look something like this. And as you can imagine, the order parameters now are much lower. Remember that the definition of order parameter is cos 3 cos square theta minus 1. And now the order parameters will be much lower because now we are in the fluid phase. So if you can measure the order parameters from a molecular dynamics simulation or from an NMR experiment, you can immediately decide whether the membrane is in the fluid phase or is it in the solid phase. This number is about here would be about 0.2, and this could be about 0.3 to 0.4. Now, let's say we have only one phase transition for simplicity, which looks like this. So what happens if we add an external molecule, a doping molecule to a membrane? Let's say you have ethanol or a drug which binds to a membrane. Then you can measure the impact of the binding of the drug on this curve, which is usually measured in a heat capacity, in a calorimeter. Let's say you have a molecule which tends to order lipid membranes, lipids, right? This could be, for example, a calcium cation which can cross-link two lipids, especially negatively charged lipids, and therefore order lipids. If ordering occurs more easily, then it will take more energy to melt this membrane, and the phase transition would probably be shifted up by a little bit. So if you can measure this phase transition temperature, you can also predict what happens what effect a molecule might have on the interface or to the lipid tails. Now, accompanied with this ordering and disordering of lipid tails is also a change in the area and correspondingly to the thickness of the membrane. You can imagine that if the lipids are perfectly aligned, then the membrane is much thicker than it would be if the lipid tails are disordered. So this membrane is thinner than this membrane. So more disorder typically means thinner membranes. And since lipids are a liquid, more or less incompressible, more disorder also leads to larger area per lipid. So the three parameters that we measure in our simulations, which are area, thickness, and order parameter, these all report about the physical state of the lipids. These two can typically be obtained from a diffraction experiment. And the order parameter is typically obtained from NMR experiments where you deuterate different carbons along the lipid tail length, as we discussed in class. So this is the reason we calculate area, thickness, and order parameters. And based on changes in these three parameters, you can also predict lipid mechanical properties, which we haven't talked about. So membrane mechanical properties such as the bending rigidity, the amount of energy it takes to bend the membrane, but this is beyond the topic for now. So this was a short note about why we measure area, thickness, and order parameters of lipid membranes.